going to say 7 years ago, BlackPenRedPen published an example of how to solve by example a problem counting how many arbitrary rectangles there are for any specified kind of like rectangular grid. So say for example I could generate a grid here that has 4 vertical lines. Actually there's 1, 2, 3, 4, 5 of them vertical lines here. And then 1, 2, 1, 2, 3, and 4 here. And he sort of showed like a technique using combinatorics how to quickly go and solve this problem. But I basically want to, in this case, video today, generalize the results. So what he ended up using, and which we will use too, which always comes in handy, is then when you're multiplying by grids, to go and find like the areas of each of the squares or the rectangles inside this grid here, you can simply take the length of each of these different rectangles here. One could say be 1 here. One rectangle could say have a length 1 here. This could have 2. And then ... extend them forever, and then this could have a length of L. Same thing here by symmetry, 1, 2, ... and then L. Well, I would need to go and like draw an additional picture to like sort of see that little additional length here. But one key thing is that the sum of consecutive integers is basically given by the triangular numbers formula. And if you're wondering where that comes from, I have a video stating how you derive this result. It's just a quick result manipulating arithmetic sequences using something that Carl Friedrich Gauss did many years ago. In any case, this term equals this result here and this result. And that would be the end of it. But I want to go and generalize this for not just areas, but say like the surfaces of volume, the surfaces of three-dimensional objects. Say for example, a rectangular prism. So say for example, you were to have, please give me a second, my mouse is glitching out a bit. You were to have an arbitrary rectangular prism here, and you wanted to count how many rectangles are formed along the surfaces of this entire rectangular prism here. So yeah, here I'm just making a quick rough sketch as possible. This might take a while. Ooh, that was a little bit nasty. Oh well, I'll have to do just to save time. Well, in that case, what do we recall? I found this simply by, in this case here, I found this as a number of rectangles simply by using the geometric formula that area of a rectangle equals base times height. But when we're looking at the volume of a rectangular prism, not volume, the surface area of a rectangular prism, we have two different possibilities of terms we can look at, because you can have essentially, and now here's where I will draw in color, you will have 3 pairs of 2 faces that are opposite each other and have the same number of rectangles on them. So say I draw like this rectangle here, it will have a pair on the opposite side here. This is filled like a grid like so, and will have the same number of rectangles there. If I were to then go and like generate like another rectangle that connects this together, say at the bottom and then the top of this rectangular prism, this would also by symmetry have an equal number of grid-like rectangles over here for this corresponding dimension. And finally, the same will apply for the height if I were to draw these purple rectangles here. So as you can see, 6 surfaces are broken up into 2 pairs of 3. So you'll have 3 terms that are being added together. That means that you'll be doubling the result of the number of rectangles for each particular edge of the surface. Now remember that surface area of a rectangular prism is, okay, 2 times length times width plus 2 times length times height plus 2 times width times height. So all we do in this case is replace the L, W, and the H with the corresponding sum of consecutive numbers here to get the corresponding triangular numbers. And boom, that gives the entire surface area of the rectangular prism. Now, a key thing that you can do in mathematics is, because this is a general result, you can look at specific cases or extreme case examples. One case could be a cube, whereby the length, the width, and the height of the rectangular prism are all the same. In that case, what happens? Well, we should expect that if we get a... oh wait, this will be a quadratic term, and this is a quadratic term here. We should expect to end up with basically... oh, I'm sorry. This is along the surface of a cube. If you're looking at the outside of a cube will have basically 6 faces if you go and break up its net open like this. One, two, three, 1, 2, 3, 4, 5, and one more 6. This one covers the top of the grid. If you fold everything up, that will be the 6th particular face. So you'll basically almost like do the same result to what is it? Yeah, 2 times basically these two quantities here times 3, because you're basically adding the same term 3 times. Yeah, so you basically get like one copy of this. This is basically the same thing as this term and this term. So you have 3 terms being added together, and then you multiply them and get this as a result, which simplifies to 6 times L times L plus 1 over 2 squared. And if you want, using like a trick of Nicomachus, this is also equivalent to the sum of cubes. But consecutive cubes, I should say. Now consider the case if the 2 length dimensions are the same, but the other is different. Say let us have a prism of square base and a different height. So L equals W, but different. You'll naturally end up with this particular nasty mess over here. And just from algebra, we get this as a work here. Now, here's the last problem, which is being represented by this particular drawing I've sketched over here. What if you want to count the total number of rectangles that are fitted inside the grid 3-dimensionally, say as a lattice here? What do you do then? Think of it like this. You cut you basically will have your 2 opposite sides, correct? This one here and this one here. And between these rectangles, you'll basically be you'll be stacking a whole bunch of other rectangles in between there that are almost the value of the arbitrary variable length you're dealing with. Not quite so much n, but n minus 2, because we're not including these 2 green lines here, which have already been counted. In this case, you would simply get L times L plus 1 over 2 times W plus 1 over 2 times the height of the rectangle. And then by symmetry, you go and do the exact same thing for 3 remaining terms you had. And if you want to express this combinatorially, you can state or understand this as saying, like, within a choice of L plus 1, because like these grids for the rectangles, not only are they rectangles themselves, they can be considered lines. So within a choice of L plus 1 lines, and you had to pick two of them, these can be multiplied by the other corresponding lengths, the height and the width and the length, and you get this particular equality. And this, just by a combinatorial argument, holds true. And yes, they multiply together by the multiplication counting principle, which allows them to become a rectangle. Now, if you want to overkill this, you could then go and use induction, but I would recommend against it, as that is a very, very ugly process. Okay, I hope you enjoyed this video, and I hope this added a bit more depth to a conversation that BlackPenRedPen already started. Okay, have a good way.